So we've talked about determining volume from slicing. Now we're going to look at another way to determine volume. Okay. And this is called the solids of revolution method. And this is like it's very similar to doing it with slicing, but it's a little more, how should I describe this? All since are forgiven and burritos involved. Yes, I like that. This method is very similar to the cross-section method, but it gives you a more explicit formula sometimes, and it actually shows you how to come up with the formula in an easier way. Like I basically remember earlier I was in the previous thing I was saying, look, if you actually have this cross-section formula, this is what you would do. Like that's not always the easiest thing to figure out, right? So this idea of what's called solids of revolution, it sort of basically gives you an idea of what you're dealing with, and and what's interesting about it is that it's always going to have like it's going to be related to circles because you're revolving something around. So it's like if you have this point right here, like if this is the height of your function, if you revolve it around, you get a circle, right? So imagine if you have a bunch of different points and they're all revolved around, it's like a bunch of circles put together. So it's a very particular case of the cross section, but where all your cross sections are circular, I would say. And this actually ends up happening a lot in the real world. Like, if you know anything about manufacturing, when they manufacture stuff, a lot of the times to make like extruded shapes, they would whirl something around. Like, does everyone know what a lathe is? A lathe is where you have like this spinning axis and you put something on there. Like they usually do this with pottery, like with a pottery wheel. You know, it spins around and you put your hand. That's making a circular cross section because you put your hand into the dough and as it rotates, it's literally making a circle, right? So in manufacturing processes, these things happen a lot, which is probably, to be honest, why it's such a common thing to teach, because we end up making volumes that have circular cross sections, right? So like hopefully you're getting the idea that like this is a very practical application through like hundreds of years through manufacturing processes. All right, so let's go to writing mode. So let's talk about surfaces of revolution, solids of revolution. Okay, so what are these solids of revolution? Well, it is very related to what we were talking about before. Like normally, let's put in our X and Y axis. Yeah? Yes, what's up? It's very similar to it. So first we're just going to talk about how do you get a solid, which will have a volume. How do you get the solid? You get it by revolving something, so we call them solids of revolution, and then we will calculate their volumes. Yeah, this is still chapter 2, section 2 in the book. Mm-hmm. Yep, no problem. So you have your X and Y axis. You have your function f of x. And actually, usually you have a region, right, where you go from A to B. Right? We could calculate the area under f of x between A and B above the x-axis, right? But now, what we're actually going to do is, so we redraw this. Here's our x-axis. Here is our y-axis. I guess I should probably move this down because it's going to get stuck. There we go. Okay, now here is our function f of x. Do you see how it's still on the xy plane? And we have our bounds from A, oops, I did that backwards, A to B. Okay, now how do you make the solid of revolution? You make it by revolving every point. Like you can imagine, like at this point right here, that green line through x equals b is your radius. and then you're revolving that around to make a circle. So the shape you get looks something like this. Right? As you revolve it around, if you revolve that radius around, you're going to get some shape that looks like this. And then if you revolve the other one around, you're going to get a shape that looks like this, right? In the sense of if you treated those green lines as your radii. Oops, okay, that's not the shape that I wanted. What the hell? I want a circle. All right, does everyone see I'm using the green lines as a radius? And let's draw in what you're going to get. So you're going to get something that goes like this. And then you have this shape. It's sort of like a bell. I can't draw it too well, but I'm going to try. If you keep on drawing in a bunch of other circles, you get this shape that gets rotated around, like so. That is a solid of revolution. At the top, yes, it looks like if you chopped off that top part of the water bottle by the cap. Yes, exactly, yeah. Which is vaguely bell-like, but I agree much more that this is a lot closer to it. If you were to draw it on the side, it looks basically like this. All right, and then that one goes around like so. And there's that top. That's that, like, shifted on the side, basically. Yes, you revolve it around the x-axis. It is very important. So if you notice, this line is coming up out of the x-axis parallel to the y, and then you rotate it around the x-axis. We will eventually have solids of revolution, which are formed by rotating around the y-axis. So instead of rotating like this, you would rotate around like that. Right? You can rotate around the y-axis by going like this, or the x-axis like so. Okay. So let's come up with our formula as to how we're going to do this. Okay, so when you do this, you call it the disk method. Okay, I'm like losing. So we're going to call this the disk method. So I'm going to show you how you get the formula for the disk method. Here's the x, here's the y. You have that function f of x like so, and you're interested in going between x equals a and x equals b. I don't know why I really had like a 6 there. And you're going to make a solid of revolution by spinning that around, yes? Okay, so remember, how's this going to work? We're going to partition the x-axis into a bunch of points, right? Those points are our xi's, and the xi's are going to be a plus delta xi. And what is delta x equal to? It's still equal to b minus a over n. Okay? Now let's choose one of those particular points to draw like an example. So here, right here, we have our xi. And if you evaluate that, you get some height f of xi. Agreed? Now, the cross-section is formed by literally revolving that around the x-axis, yes? So if you literally revolve that around the x-axis, you get some shape that, oops, okay. Sometimes the computer just doesn't want to let me put in the circles. It's like driving me crazy. You get this circle like so, right? Now that circle has some cross-sectional area. What is the rate? So what is the formula for the area of a circle? the area at xi is going to be what? The pi r, right. So pi r squared, right? But what is our radius in this case? It's not xi, it's what? Yeah, exactly. So you get pi f of xi quantity squared. That is your, because you know the cross section has to be this because you're doing the solid of revolution. Now, we're not interested in adding up areas, we're interested in adding up volumes. So what do I need to do to this circle? I need to extend it by some amount and basically make a cylinder. Now, how much am I going to extend this by? Is my question. Yeah, exactly. So your volume for that at xi is going to be the area, which is pi f of xi quantity squared times delta x. And then remember how I said you're going to have to make your formula? This is now your volume formula. When will this be applicable in life? I just talked a bunch about manufacturing and junk, so RE, what I said 5 minutes ago. So now that you have one of these singular little volume estimates, how do you estimate the whole thing? By adding up a bunch of different ones through your partition, right? So what does that mean? Well, you're going to do the sum of sigma I equals 1 to n of your volume formula, which is pi f of xi quantity squared delta x. So that is going to be your estimated volume. And then remember, what did we do with the estimated whatever previously to get the actual area? Holy crap, you take the limit, that gives you a definite integral. So you're like, okay, I'm just going to do the limit. I'm going to let whatever those little cylinders are, I'm going to have an infinite number of them to estimate my volume. So I'm going to do the limit of sigma I equals 1 to n of pi f of xi quantity squared delta x. That is the actual volume. But more importantly, how am I going to calculate that? Well, with a definite integral from a to b, where this is the function that I'm integrating, which is quite simply pi f of x quantity squared dx. Bam. Yeah, like what Michael said in the chat, there's like tons of stuff with carpentry, extrusion, like America's a war machine and we export violence elsewhere, and that requires, planes and trains and ships. It's what we're good at. It's welcome to the machine. Your services are required to create stuff. There you go. So anyways, this is the disk method. So let me show you an example of like how you would actually do this. I like how your response is understandable. Now you know why. Actually, to be honest, a lot of this stuff is used in like shipbuilding. Like if you need, like back in the day, like when this was actually invented, you would make pieces that would be in ships. Like that was like, there were no planes and stuff, right? So like creating big wooden vessels was the height of technological excellence in the 18th century, right? Interesting thing, how did the British conquer the world? Because they had ships that went everywhere, right? So they knew all the crap that was going on. Like, if you're of Indian descent, you're really familiar with what the British are capable of. Oh, yeah, and SolidWorks and stuff, like, definitely. Like, they still do all of this, but, like, I'm just trying to say, like, historically, like, they know, actually, for a fact that a lot of this was making very complicated pieces to put into, like, actual wooden ships. Yes, they did. Because like here, just quickly talk about ships. You have to does it make sense? Like your boat, like that's the cross section of it. Now, what happens to the boat as you go further? It closes to the bow, right? So you need to figure out how the timbers change. So one of the things of this is like you need to figure out exactly how much wood you need as the ship gets smaller. before they'd be like, I don't know, it's about this, and they'd get too much wood or not enough wood. With this, you know, like, I literally, this is how much I need. And that, like, makes it so you can do everything faster. There's no, like, oh, crap, I got not enough wood. The boat is delayed for until a year from now where the wood will arrive. So yes, like what's happening in the chat, like, you know, a lot of this they straight up use this to be efficient. It's about how efficient they are in the use of their resources. They're not like superhuman. They just thought about crap unlike everyone else, and that allowed them to do a lot. So anyways, let's do an example. I mean, you have to give it to them. They're very clever. I'll say that. As someone of British descent, you know, boom, there you go. Partially at least. So let's calculate the volume of a solid of revolution on the interval 1-4. I can't type interval 1-4 for f of x equals square root x. Oh, you guys are in the chat are hilarious. So, let's just draw the picture. What does this look like? Oops, I can't draw a straight line. Here's our y-axis. Here's our x-axis. The square root function looks something like this. We're going from 1 to 4. Let's revolve it around. Boom. Okay, not what I wanted. Okay, I wanted to move that one. There we go. Okay. So you get this, oops. You get this, looks like the Apollo space module. Or like a gumdrop. If you're familiar with gumdrops, right? You've got like this gumdrop shape. What's the volume of this thing? So, let's go through and like actually set this up. Like, if you choose some point xi, you're going to revolve that around. So notice I'm actually like going through like how do you do this, right? So you revolve that xi around, and then you're going to have to extend that xi, which gives you this this disk. That's why it's called the disk method. Does it make sense? Whenever you revolve that circle around and extend it, that's a disk. You could call it a circular prism, right? The disk is the circular prism. So one of your volumes for this disk is pi f of xi squared delta x, right? Now your function here is the square root, so you're going to have the square root of x quantity squared, right? Now because we're going from 1 to 4 and x is positive, the square root of something squared will just be a positive number. You don't need the absolute value of the number. So they cancel and you get pi x dx. There's your volume formula. So for one of your disks, right? Now how's your integral going to work? Well, you got to do the sum of those disks, right, to get the estimates. You're like, okay, well, I'm summing I equals 1 to n of pi x. Oh, this is not dx, this is delta x. That's your estimated area. Once again, I'm going through the bother of actually writing up all the steps to get to the definite integral, because in a physics problem, this is the hard part, and everyone's like, oh, why don't you just jump to integrate pi x dx right now from 1 to 4, because sometimes it's going to be a little more involved. So what's the actual area equal to? Well, it's going to be the limit as n goes to infinity of your sigma I equals 1 to n. And actually this is xi right here. So pi xi delta x. Right, because we had the xi. I forgot about the I earlier, my bad. Because we weren't plugging in x into f, it was f of xi, right? Now, this becomes a definite integral. Our bounds were 1 to 4. The function we're integrating is just pi x dx. And then, yeah, now we can just find the antiderivative. That's pretty straightforward. The antiderivative of pi x is pi x squared over 2. So we want f of 4 minus f of 1. We can factor out that pi over 2, right? Because it will be in both of them. So then we're going to have 4 squared minus 1 squared, which is going to give us pi over 2 times 16 minus 1 is 15. So whatever 15 pi over 2 is, there's the volume of that shape. Boom. Notice once you get to the actual definite integral, it's not that bad, right? The complicated part usually is setting up the problem and understanding why this works. Because you get that cross section of the circle, right? That's why you have the pi f of x squared, and then you have to extrude it. That's why you multiply it by the delta x. That's how you get your volume function. Well, yeah, I mean, it's not that bad so far, because like this is like an easy example. Like, believe me, like, okay, so pretty cool thing. Does everyone know like what work is? Like the physics concept of work, it's force times distance. Like you can calculate the work of having to suck up water up a straw. Yeah, you actually have to use this to calculate that. Now imagine like work doesn't seem like a volume, right? You're gonna have to set up this formula where you incrementally estimate the amount of work at a particular point, and then like actually going through this then is like, holy crap, if you haven't spent a bunch of time, you're like, I don't know what's going on anymore, and my life is a lie, you know. So yes, these aren't that hard. We're literally going through so you can like see like, oh yeah, that's pretty straightforward. Like you set up this formula, you take the formula and you sum it, and then you just take the limit of that sum, and then you convert that into a definite integral. Not that bad. Like it gets really hard for some of those questions because you just look at it and you're like, I have no idea what I'm doing. Like, what is it that I'm estimating? You know, and like, if you could think about it in terms of I want a volume, so I need to come up with a formula for a volume at the point, and then I'm going to add up all those different volumes at those different points in my partition. That's why I'm summing. And then I'm going to take the limit of that, and that turns into a definite integral. Like, you have a good idea of what's going on. Yes, we're all in a simulation. It's pretty nuts. Or we probably are. That's like what I think at this point. Okay. So, now we get to talk about if you revolve around the y-axis. Okay, like these are tough. So what now if what about revolving around the y-axis? I mean, it's pretty similar, luckily, but it's a little more work. Okay, and I guess we'll just do this with an example. Oops. So, example, we're going to calculate the volume of the solid of revolution about the y-axis on the y interval 0 to 4. So remember, before the interval was x values, these are now y values, for g of y equals the square root of 4 minus y. Okay, so there's my x and y axis. Here's my x. Here's my y. The square root of 4 minus y. So remember that's x equals the square root of 4 minus y. It looks like this. It's like the square root of y would look like that. Actually, okay, let's actually go through and show you how you would do this. This would be the square root of y. Actually, oh no, my bad. This would be the square root of y. We want the square root of 4 minus y. What do you do when you put a negative in front of your independent variable? It flips it over the axis, right? So minus root y looks like this. Now, this is adding 4 inside, which moves it 4 and yeah. So it's going to be up here. So that's the function that we want. So I'm just going to erase the other ones, but now you know why it looks like that. Oops. So it looks something like so. Okay, so you get square root of 4 minus y. Now we're only interested in revolving it from 0 to 4, so this is the stuff that we're revolving. Now when you revolve this, you're revolving it around the y-axis, so you're going to get something more like that. So you get like, again, this sort of like gumdrop shape. I know I'm not really doing justice to it, but good enough, right? Hopefully you can see that as you revolve around the y-axis, you get that. Okay, so how does this work? There's like several ways you can think about this. We're gonna insert an axis. Okay, it doesn't want to let me do it. One, two, three, four. 1, 2. Okay, so this is the part that you're gonna be revolving. Okay, so this point right here is gonna be my xi. Or sorry, yi. Right, because we're revolving around the y-axis. Okay, there we go. So this length is square root 4 minus yi. Okay. And you can create a rectangle How fat will that rectangle be? Delta y. So does everyone see it? Instead of revolving first, I fattened my little line to make a rectangle. And then what am I going to do? Then we rotate it around to get our disk. It doesn't matter in which order you do it. It works exactly the same. But the way you can think of this is that you're taking your rectangle and then you're revolving it around. It works exactly the same. So what's the volume of this? Your volume at yi is pi square root 4 minus yi, because that's your radius, and you have to square the radius, and then you extend it by delta y. Which can be simplified to, once again, because all this is positive, what happens with the square root and the square, practically speaking? They cancel, right? So you get pi 4 minus yi delta y. That's the volume of one of those things. Now, you would do that a bunch of different times for all those different disks, so you would add them together. So you get sigma pi 4 minus yi delta y. That's the estimated area. What's the actual area going to be? Well, you take the limit of that. So the limit as n goes to infinity of sigma I equals 1 to n of pi 4 minus yi delta y. And then what's the payoff? You realize that you're just going to integrate from 0 to 4 pi 4 minus y dy. Boom. That's something I can now solve using all the integral stuff that I've learned. To make life a little easier on ourselves, let's just distribute that. You're going to get 4 pi minus pi y. Sounds weird to say that. 4 pi minus pi y. Sounds like a tongue twister. Okay, but you need your antiderivative. Your antiderivative of 4 pi will be 4 pi y. And the antiderivative of minus pi y will be minus pi y squared over 2. I feel like I'm doing tongue twisters. 4 pi y minus pi y squared over 2. Imagine if you're not a native English speaker, it probably sounds like nonsense. Actually, I'm thinking about that right now. That would really suck. It'd be like, what is he talking about? Okay, so now you need f of 4 minus f of 0. Oh my god. Okay, this is going to be horrible. Okay, now we got to plug these in. So we're going to get 4 pi times 4 minus pi times 4 squared over 2. That's f of 4 minus 4 pi times 0 minus pi times 0 squared over 2. Thank God all those zeros. Wait, how do we think it's foreshadowing the rest of it? I'm like wondering now. All those things cancel. Oof. Okay, so what are we going to get? 16 pi minus 16 over 2 will be 8 pi. Wow, it just becomes 8 pi. Boom. So apparently, what is the volume of that thing? It's 8 pi units cubed, whatever the units are. You might be wondering, like, why would you care about this? If you need to create some piece of metal, like you're forging it, you need to know how much metal to start with to get the shape that you want, right? You don't want to like pour in a bunch of molten iron into your cast, and then all of a sudden you're like, oh, I had too much, or I didn't have enough, and the piece isn't big enough, right? So is that sort of making sense why you would actually be interested in calculating volumes, especially if you're like making things with metal? Yes, all the pie eating. Okay, so I've shown you now how to do the disk method with revolving around the x-axis and revolving around the y-axis. Notice it doesn't really make any difference, right? You're still using the same volume formula where you're rotating a disk around. You just have to be aware that you're using the right type of function. Yeah, it's super helpful in 3D modeling. Computers just do this automatically now, like for you. Like when you're using like SolidWorks and all that stuff, like you make it and it can just tell you what the volume is because it knows the functions that you gave for all the different things. Okay,